Hello everyone, welcome back. In this module, we will talk about the techniques and technologies for the sediment management in inland water transport. In the previous sub-module, we have seen how sediment monitoring is very much crucial in the inland water transport operations. For this, the sediment transportation and the distribution of the sediment needs to be monitored thoroughly. We have basically two types of sediment loads, the bed load and the suspended load transport. The bed load transport depends on the shear velocity of the bed and the effective resistance of the sediment particle. The suspended sediment flux is calculated by multiplying the average current velocity and the sediment concentration. Thus, essentially, if we can measure the average current velocity and the sediment concentration, we can get the understanding of the bed and suspended load transport in the particular current, and through this we can monitor the flow of the sediments that are there. Now for this, various systems can be utilized. For example, an acoustic Doppler current profiler is an instrument which can measure both the quantities of current velocity and sediment concentration from a vessel. The direction of the sediment transport can be detected using geomorphic indicators or by tracking movement of artificial tracers. Computer-aided wave refraction studies can determine the places of wave convergence and divergence, which provide a quantitative measurement of the littoral drift and the direction in the local and regional areas. There are sedimentological methods of analyzing the sediment transport, which include the determination of the sediment budget. Sediment trap study is another technique which is employed to measure the quantity of suspended sediments in aquatic systems. The remote sensing studies on these various landforms can provide reliable long-term drift information and can be conducted quickly. Then apart from that, there is the sediment transport modeling and monitoring, and is gaining importance in the recent times as theoretical field and laboratory analysis often prove inaccurate and misleading to the complexity of the process and large number of controlling parameters. Then there are some other kinds of innovative techniques as well. So there are various erosion control techniques which include the placement of large rocks along the banks or river banks to prevent erosion. Have been use of geotextile, which are synthetic fabrics used to stabilize soil and prevent erosion, which would decrease the sediment influx into the water systems. There are also sediment bypass systems which include various tunnels to divert sediment-laden water around the critical infrastructure such as dams to prevent the sediment buildup. Control release of water to flush out the sediment from reservoirs or other sediment accumulating areas is also done using sediment sluicing. Then there are the innovative technologies of environmental dredging, which is low impact dredging techniques to minimize the environmental disruption. We can also use microbes to generate electricity from the sediment, which can help in sediment stabilization. Water injection dredging is also used, which used water jets to resuspend sediment into the water column, allowing the natural currents to transport it away. Then there are sediment traps and basins, which are settling ponds found by the excavation and an embankment that can intercept and retain sediment-laden runoff from a particular site for a sufficient period of time to allow for the majority of the sediment to settle down. Proper use of these structures can greatly reduce the sediment transport, and if properly designed, installed and maintained, sediment removal efficiency of 80% or greater can be achieved, but again it depends on the various soil particle types and the other sediment characteristics. In case of excessive sediment buildup, we also have to opt for sediment removal. In this, various pumping systems or dredgers can be used. In the figure, you can see a hydraulic pumping system which is used to remove accumulated sediments from the reservoirs or to river systems in order to be flushed elsewhere. Now, based on the type of dredging, type of the sediments that are there or the local conditions that are there, we can choose a number of dredging schemes. Now, four broad classifications can be made based on the mode of excavation and operation. So there can be mechanical dredgers, hydraulic dredgers, or mechanical hydraulic dredgers which utilize both the basic elements in some combination, and then hydrodynamic dredgers. Within these four categories, further subdivision can be made on the basis of the propulsion, that is those are self-propelled either during the excavation phase, the transportation phase, or both. And then the stationary ones, the production rates for the dredgers can vary depending on the circumstances that are there, the methods, the material to be dredged, and the transport of the disposal methods that are employed. Now, based on all of these factors, production rates can range from 50 cubic meters to around 5,000 cubic meters per hour or more. Now, dredging guidelines for major ports and inland waterways with standard operating procedures are issued by the Ministry of Ports, Shippings and Waterways. However, the government has not been able to implement advanced dredging strategies to maintain the local and regional sediment levels, and these are some areas which with fine grained dredging, as the majority of materials from dredging is unsuitable for recharging the marshy areas due to contamination. Also, apart from the routine maintenance dredging, the Dredging Corporation of India is another authority which collaborates with the government on the capital dredging, reservoir desilting, waterway dredging and all. Additionally, it also assists the government in coastal development projects, employing the dredged materials, conducting surveys and undertaking the geophysical and geotechnical works. The dead material can be thought of as a resource. Project developer can easily use this dead material in an effective and economical manner, especially in an inland waterway which requires frequent dredging. Dead sediments again, they can be classified based on the geotechnical or the engineering properties and can be used to for another critical infrastructure development. But again, it all depends on the properties of the dead material. If the material is sandy or rocky, it may make an excellent fill for land reclamation, or else if it's cohesive and muddy, it might be used for landscaping or for improving the agricultural land which lies near the waterways. Now, over the past 2 years, there has been a revolution in harvesting the potentials of AI by different organizations around the globe. And with the advent of 5G, big data, Internet of Things, the data can be easily and safely shared in the real time among the interested groups of researchers. So, if we have the data accumulated from one dredging project, it can be shared with the various stakeholders in other projects. Using the big data, the operators in other projects can understand the patterns that might be necessary to reduce the cost and efficiency of the dredging machines. During the dredging operation, systematic monitoring of each load can be performed according to the contamination of the sediments and reuse suitability, which would allow for a better management of the selective storage and processing of the sediment stocks. The environmental impact of these dredging operations can also be better monitored by having an on-site real-time analysis, especially for the water, like the turbidity and the contaminants, rather than having a laboratory analysis on the various discrete samples that are being pulled out. On-site analysis allow more closely spaced and more frequent analysis than sampling and the laboratory analysis, which would allow for a quicker feedback and are better understood by the communities and the various authorities. However, the dredging on the national waterway represents a number of technical challenges, including the logistical concerns regarding transportation of fuel materials to the dredger, heavy siltation, and the recurrence of the sediments that are there. So, major challenges would include the increased flood risk in downstream areas, frequent changes in river courses, morphological issues, difficulty in identifying the disposal grounds, strong currents and rapid changes in water levels and reduction of flow discharges, increased bank erosion issues, and difficulty in maintaining the dredging depths in upstream areas. Moreover, there are challenges on the on-site analysis that we talked about. These cannot reach the accuracy or precision of the high-quality laboratory results and therefore cannot be used for compliance reporting if the results are close to regulatory thresholds. They are also sensitive to variations and can be used to improve the representativeness of the regulatory samples. Thus, the laboratory confirmation would be required for this on-site analysis. Also, the on-site analysis would not lead to the determination of the majority of the parameters that are required for understanding the strength or other characteristics of sedimentation. This is of prime importance for the risk analysis, and hence laboratory analysis would be required. Also, some of the analysis that needs to be considered for decision making cannot be analyzed directly by the on-site techniques. Hence, there are a lot of challenges in developing the on-site techniques as well. Hence, so the way ahead would lie to have this modern technological interventions which would integrate the local conditions that are there. For this, we can have various acoustic surveys, various local research studies to understand the local dynamics that are there, and to develop a future prediction and modeling framework for sediment distribution and the sediment modeling. Now, with this, I'll end the discussion here. Thank you.